Alright, we're just going to go over concept check your understanding questions 8, 9, and 10, have a little discussion about it via you just simply listening to me talk. The first question is more elastic potential energy stored in springs when the spring is compressed by 1 centimeter than when it is stretched by the same amount? Since the formula for potential energy spring is 1/2 kx squared and the displacement is being squared, it doesn't matter which way it's being compressed, you're going to end up getting the same. Whether it's negative 2 centimeters or positive 2 centimeters, you're going to end up getting the same potential energy. So there is not any more potential energy if you stretch it versus compress it. You get the same amount. For number 9, a block is attached to the end of a horizontal ideal spring and rests on a frictionless table. The block is pulled so that the spring stretches relatively to its unstringed length. In each of the following 3 cases, the spring is stretched initially by the same amount. Rank the amplitudes of resulting simple harmonic motion in decreasing order, largest first. A says the block is released from rest. B says the block is given an initial speed. C says the block is given an initial speed of 1/2 v naught. Whatever kinetic energy it has, it's all going to be changed into potential energy. So the more kinetic energy you give the block initially, the farther it is going to stretch out. So pretty much it's like, if you can even visualize it in your head, imagine you throw a ball and the ball is attached to a spring. Is the ball going to go further the faster you throw it or the slower? The faster you throw it, the further it's going to stretch, the more potential energy it has. So the order is B, C, A. Kinetic energy initial is proportional to the potential energy final. Kinetic energy goes up, potential energy final is going to go up, as it is all being converted. Number 10, a block is attached to a horizontal spring and slides back and forth on a frictionless horizontal surface. A second identical block is similarly attached to the first block. The attachment is accomplished by joining the blocks at one extreme end of the oscillation cycle. The velocities of the block are exactly matched at the instant of joining. Alright, so you're pretty much attaching another mass at the point where they're reaching, at the point where the oscillation is at its maximum amplitude. In terms of the potential energy of the spring, if you attach at the end of its amplitude, there is no kinetic energy. The kinetic energy has dropped to 0, and then you add this mass. But adding the mass doesn't really change the potential energy in the spring, because the potential energy of the spring is based on how stretched out it is. And since the mass doesn't play into the factor of how you calculate your potential energy of the spring, adding that mass does not change the potential energy of the spring at all. Because your potential energy is not going to change, when all that potential energy gets changed back into kinetic energy, your kinetic energy is also not going to change. But kinetic energy does depend on mass. So if your initial kinetic energy didn't change, but the mass doubled, that means your velocity had to have decreased by a factor of square root of 2. Square root of 2, not 2, because the velocity is being squared. So the velocity, the amplitude is the same, because it's still going to, once all that kinetic energy is going to become potential energy, it's going to end up at the same final displacement. The frequency, which is equal to 2 pi, which is the inverse of the period. So if the period is 2 pi square root of m over k, then the frequency is square root of k over 2 pi square root of m. So if you double the mass of an object, the frequency is going to change by a factor of 1 over square root of 2, or it's going to decrease by a factor of square root of 2. So that's what happens to the frequency. And the maximum speed, well, the maximum speed is going to decrease. That's actually a mistake. It's going to decrease by a factor of square root of 2. We'll fix that right now. There we go. The velocity final, or the maximum velocity, is going to decrease by a factor of square root of 2, or it's going to be 1 square root of 2 of the original amount. There we go, that's better. And that ends that.